right, we are back for part two of passive solar heating design. This is a sun space. It's what we call an isolated gain system. That is, the area that's collecting the heat is completely isolated from the rooms that are being heated. The sun space is essentially a room, like a greenhouse, let's say. It might be a conventional word if we're more interested in growing plants. But in this case, we call it a sun space because that emphasizes its primary role in collecting and storing heat in a passive solar heating system. So the idea here is that we're going to concentrate all of the area where the heat is collected into one space. Therefore, some of the other spaces in the building can be freed up and not have to have so much glazing area. We're also going to maximize the amount of thermal storage that we have in that space. So instead of just maybe one surface being massive, we're going to have as many surfaces as possible be massive so that we can make sure to store and capture all that heat that's coming through the glazing. This sun space then becomes like a servant, you might say, in Kahn's distinction between servant and served. So the sun space is the servant. The rooms that it heats become the served spaces. The sun space has lots of kind of constraints on what it can be, and then it frees up the served space to have a lot more flexibility, although we do like to still see some thermal storage in some of those spaces. The heat transfer is by radiation primarily, although it can certainly be by convection. We can have doors and windows and vents opening into the sun space. The sun space itself, though, is not heated mechanically or cooled, so we have to be careful about that. Otherwise, it doesn't become a functional sun space. Here is a sun space, which is a combination of a greenhouse for growing plants and starting seeds and so forth at the Missouri Botanical Garden in St. Louis. It's also a sun space, and the building is a passive solar heated building. You can see the exterior of the sun space on the upper left. So it has a roof, a south wall, and an east-facing wall that are glazed. The east-facing wall, remember, is not really providing much winter solar gain, but in this case it would be providing extra light to the plants. On the lower left, you can see that a shading layer has been pulled down. Now that could be important both to reduce the excess heat gain or excess light to the plants, but also if it's summertime, you don't want that extra heat coming into the space. You can see that the floor is covered with a tile that's sitting on top of a concrete slab, so it's a massive floor. And the back wall is actually brick. The brick wall has openings in it though. So in the upper right, you can see the wall that's in between the sun space and the rooms behind it. Part of that is because it's an exhibit, so people can see into the sun space. But also there's regulating windows that can be opened manually at the bottom and in the middle. And then at the top, they're automatic because it would be too hard to reach up there. So those are switchable and they can be also put on thermostats. So that allows the convective regulation of warm air to be either cut off or circulated between the sun space and the room behind it. So if the sun space is really warm, the space behind it is too cool, you can open those windows and let the warm air flow over into the space. When it gets warm enough, you can cut them down. On the lower right, you can see some little exhaust fans. So one of the things that happens in the summertime is the lower windows get opened. You can see that on the upper left slide and on the lower left slide also. And then those exhaust fans come on based on a thermostat if it's too warm in there, so that we're sucking out the warm air and not letting that come into the space behind. So in the summertime, we would certainly keep the windows that you see in the upper right image, we'd keep all that closed. This was one of the first sun space houses that was really built as a passive solar collection system in the United States. This is the Balcom House. Balcom was a scientist at the Solar Energy Research Institute, SERI. And so he built this out in Los Alamos, New Mexico. You can see it's a kind of adobe house, right? And it's actually kind of rotated so that sun space that you see is kind of slicing off the plan of the building and facing south. And then all the rooms are wrapping around that at two different levels. On the right is 3 days of temperature monitoring for this house, which was built in the late 70s. So let's look at the outside to begin with. You can see that the temperature goes down at night on the first day there, down below 20 degrees. It comes up to near 50 degrees. It goes down again, comes up again, right? So there's an up and down, and quite a range, 30 degrees or so of range of temperature between day and night. That'd be characteristic of a desert or semi-desert climate. Then you can see the greenhouse itself, or before they called it a sun space, they're still calling it a greenhouse. And that greenhouse temperature goes down to about 60 degrees at night and up to about 80 degrees in the daytime. 80, I'm sorry. And then even on day 3, February the 4th, it goes up into the 90s just for an hour or so. So they must have had an intense amount of sun during that day. So sometimes that sun space is going to be too cold to occupy. If it's 4 o'clock in the morning, maybe you don't want to be there when it's 58 or 60 degrees. But in the morning and the middle of the day, it's probably pretty comfortable. By the afternoon, it's starting to get too hot. Then as the sun goes down in the evening, it becomes comfortable again. So that's one of the principles, is that you let the greenhouse or sun space do whatever it does, right? And you don't try to occupy it 24 hours a day, because if you did that, you'd end up having to air condition it and heat it, which would really defeat the whole purpose. But you also see the temperature profile for the house, which is really staying within a comfort range. It's dropping down to say about mid 60s and going up into the 70s. And these are winter days, right? So the house is actually floating, but it has a lower amplitude, right? And the idea is to keep the house within a range of the comfort zone that you could tolerate and be comfortable at. Maybe you have to change your clothing just a little bit, um, but you can see those three curves really illustrate what we're trying to do with any passive solar building. This is a German building. It's in Berlin, and it uses a series of different passive solar heating systems. On the upper right, you can see the two-story sun spaces, or what the Germans often call a winter garden. Um, the building also uses some direct gain. It also uses some air collector walls or thermal collector walls, which we'll talk about in just a little while. Up on the top of the building, those angled sections you can see, those are producing solar hot water for showers and washing dishes and so forth in the apartments. And you can see in the plan that um, the little sun spaces can be closed off from the rest of the building. So you're regulating again the temperature changes between the sun space and the rest of the house rooms that are served by the sun space. Exterior facade. And one of the nice things you can see about passive solar design is that each one of the systems has a different kind of characteristic of transparency. So some things seem more opaque. The wall is opaque, but then you can see the dark looking glazed sections in between the sun spaces. Those are the air collector walls. They're not admitting any light into the space. They're only used for heating. The sun space is a kind of in between, right? It's a layered space with multiple layers of glazing and walls, and then the direct gain. So I like that characteristic, and they're getting some jazz and some fun in that facade too. This farmhouse building, built in Arkansas from about 1987. This was actually built by 5 Kansas State architecture students, Bachelor of Architecture students, as their thesis project. And again, it uses a series of multiple systems, direct gain, and also a sun space. You can see that big section in the middle is a sun space. The upper dormers would be direct gain. A little sloped skylight at the top facing south. That's mainly for getting heat out of the multi-story space, but it's also good for bringing in just a little bit of extra southern sun. There's the plan. You can see on the main level, the lower section there, what they call the greenhouse. That's using both some stone, so the exterior walls that the windows sit on top of are stone. Then there's a stairwell, which is built out of stone. And then it says water storage tubes. So water is also a really good way to store heat. In fact, water stores about 4 times as much heat in the same amount of volume. So if you're going to store a certain amount of heat and you need, let's say, 1 gallon of water, you'd need about, or let's call it a cubic foot. Let's say you need 1 cubic foot of water. You'd need about 4 cubic feet of concrete to do the same job. And you'd have to spread that concrete out into a thinner area, say about 4 or 6 inches thick. Whereas the water you can just have in a container because it transfers the heat much more rapidly in and out of itself than does a massive material. So those water tubes are just sitting there. They're enclosed. In this case, you can't see them, but the heat is just goes in and out of them as necessary. Now, what if the building doesn't have a long south facade? So here's a site which had a narrow front to the south. This is kind of an eco-construction training facility. It's in Germany, and it uses a sun space on the narrow south-facing side. Now, as you can see, it's they're interested in vaults and a certain kind of rhythm and construction, and so the sun space is not, let's say, optimized. It's got east-facing glass, it's got west-facing glass, it's got glass that faces straight up. It's also got a series of louvers on top that allow that sun to be controlled in the summertime, and that sun space can be vented out. But the key thing here is that it's collecting on the south end of the building, and then it's integrated into the mechanical system. So it doesn't really, for all that glass, you can't even put enough mass in that building, even though it's got a mass floor and a mass wall, right? It's got a ton of glass. And so that, if left all by itself, that room would overheat. But what they do is then take that extra heat, integrate it with the mechanical system, move it back into the shop spaces behind and into the classroom spaces that you see on the left side of the upper left image there. So the point is that you have to move the heat from the rooms that are collecting the sun over to the rooms that don't have an opportunity to collect sun. On the left-hand side, you can see the kind of performance that you could get out of a sun space in a residence. And this is a sun space with no night insulation. So Knoxville is in there in that zone that says 50 to 60%. And what they're measuring there is something, it's a term we call solar savings fraction. And that solar savings fraction, if you can think about it very simply as the amount of heating energy that's coming from the sun on a seasonal basis, right? So what fraction of your heating need for the building is coming from the sun? Now that is in comparison to a theoretical building, which is just like the building that you're considering, but isn't passive solar heated. So that's the kind of technical definition for it. But in simple terms, it's what proportion of the heat for that building is coming from the sun. So if you had a sun space in Knoxville, Tennessee, in a residence, could be 50, even 60% of the sun, I'm sorry, of the heating, and that's with no night insulation, which means you got that R2 window glass and you're not doing anything at night to help keep that heat from going back out. If you did, or if you had a high R window, then you would typically get better performance than this. So even better. The fourth system we call an air collector. Sometimes we call it a thermal air collector. There's a lot of different specific names for it. Originally, it was a completely passive system where we tried to use natural convection as a way to move the heat into and out of the storage. And so you see that diagram on the left, that would have been from probably the mid-70s. And the main point here is that you always are using some type of engineered, designed solar heating collector, which is not necessarily part of the building structure, but could be, right? So in that lower, in that diagram on the left-hand side, the air collector is down low, right? And it's completely separate, really, from the space and also separate from the storage. So the sun comes in, comes through a glass plate, hits a metal collector, right? That metal collector is an absorber, right? And it's coated, it's painted dark, um, and then it warms up the air. The air is going down both sides of it. Warm air is rising, cool air is falling. And then in this scheme, it was then circulating through a pebble bed or rock bed, if you will, with big rocks and air spaces in between. And then there was another passive loop of air that was going into the space with dampers that could be controlled and so forth. That's a really hard system to make work effectively. Some of those buildings worked, some of them did not work at all because it's pretty hard to make air make right-hand turns when it doesn't want to and things like that. So later on, we began to add fans to the system, and that tended to be much more predictable. On the right-hand side, you see a very simple air collector down below a window. This is at the visitor center or gift shop for the Biosphere project. And all they have is just a little damper at the bottom and damper at the top on the inside wall, and it's just letting that warm air come into the space so they can turn it on, turn it off. These are really good systems for retrofits, particularly in things like poorly insulated masonry walls, as long as they're facing towards the sun. So here you see a nice retrofit going in an apartment building. Here's one where the air collector is on the south facade, and you can see that it's just hooked into the mechanical system. They're blowing air up in that cavity, and they can turn the air on, turn the air off. And because there's no glazing that's facing the interior, you're not losing any heat back out at night. So that's a bonus for it, and that's why it tends to be used more in cold climates. Here's another variation of the air collector. In sun, wind, and light, this is called a breathing wall. It's also known as a transpired collector. This is only for the fresh air. It's only heating up air that's coming into the building as makeup air or as fresh air for breathing that's required by the code. So as you remember, depending on the occupancy, certain rates of fresh air are required per person. So you can see on the slide on the left that there's lots of little perforations. And that's just a kind of corrugated metal cladding system with an airspace behind it. It tends to be dark, it's absorptive, it warms up in the sun, and the air is then sucked in kind of a slow movement and gets warmed up as it moves into that cavity behind the metal collector. And then from there, it's just taken into the interior. So it's really good for a building that needs a high level of fresh air. It's a one-through system, so it's just bringing in and it's like a preheater for the incoming outdoor air. This is back to the more conventional kind of air collector. In this case, it's being used in a farm building. It's being site built, and you can see the kind of modules on the lower right. There's inlets at the bottom and outlets at the top. And then when that module gets in place, it's covered with glass, as you see on the upper left. Okay, let's talk about passive solar glazing area recommendations. So how are we going to size the solar apertures? This is from the sun, wind, and light strategy called solar apertures. And let's see, I think I have a blow up of that, but I wanted to give you the big picture there. So let's zoom in here and just look at a couple of these. So let's take Knoxville, Tennessee, for instance. Notice the left-hand side has a 0.09 to 0.18. That's the area of glass to the area of floor ratio. So how much glass to how much floor area in proportion? So 9% to 18%, if you think about it that way. That's the guideline. The upper end of the guideline tends to be set by trying to minimize the possibility for clear day overheating. That is, if you have more glass than that, you have to be really, you can do it, but you have to be really careful about how much thermal storage you're going to put into the building. Now, on the right-hand side, you have the approximate solar savings fraction that might be able to be achieved by that much glazing area. So remember that solar savings fraction is the proportion of the seasonal need for heating that you get from the sun. There are two major columns there under solar savings fraction. One is no night insolation, and the other says R9, night insolation. We will qualify that by saying that now we have windows that might be called super windows. We can get an R5, even an R8 window, right? The higher the R of the window, the more money you're going to pay for it, but it's available. We can also do some combination. For instance, an R4 or an R5 window is not out of the question, and we can easily add to that a night shade or night insulating curtain that might be an R3, R4, not too hard to do. R9, what that means is that, if you think about it, that's a couple of inches of rigid insulation typically. So that tends to be more of a shutter or something that's really a high-tech system. Okay, let's take the no night insulation column. We can associate the 0.09 or 9% glass to floor area with a 20% solar savings fraction. If we double that glazing, again with no night insulation and an R2 window, our performance goes up to 33%. Now, it doesn't double because that's a fairly low R value window and it's also losing heat at night. But look what happens when we add the night insulation or we have a super window. Then we go from that 9%, which produces 20% solar savings fraction, goes up to 33. Same glazing area, we're just insulating at night or using a better R value window. If we have the 18%, then that 33% solar savings fraction with no night insulation bumps all the way up to 56%. Pretty good. And it doesn't really require that your building turn into a solar machine. So that's how we size solar aperture. You can go up or down a little bit from that. I wouldn't go 50% different, but if you want to add 10 or 20% to the high end and get a super, good performance, that you can do that too. This is a nice way to visualize the difference between having no night insulation and having an R9 night insulated window, or again, the option of a super window or a moderate window plus some moderate night insulation. Let's take a look at, for instance, Nashville, Tennessee, right? So the solid line for Nashville shows us going from a solar savings fraction of about, say, 19 up to about 30. That's if we have no night insulation. If you slide up from that, you see the Nashville line that has the dashes on it. And there we're looking at, let's say about 33% on the low end. And if we have more glazing, we're up in the 55% or so, right? So those two lines show you the difference between a kind of a low performance solar glazing and a higher performance solar aperture. Now look at Madison, Wisconsin. If we take the solid line from Madison, you can see that you can keep adding glazing forever, and it barely impacts the solar savings fraction because you're adding more glass, so you're collecting more sun, but you're also adding a low performance glass, so you're losing a lot of heat, especially in the cold Wisconsin winter night. But look what happens when you go to that high performance solar aperture on the dash line. It makes a huge difference. So you go from an SSF down in the teens, up to one that's over 50%, even if you're only using 20% area of glass to floor. If you're using more glass, even in cold Madison, wow, you're up there above 70% solar savings fraction. That's phenomenal, really, really amazing. So On the other hand, if I'm in Santa Maria, California, all the way over on the left-hand side, a kind of Mediterranean climate, then it doesn't make all that much difference, right? I mean, I'm getting an extra 10%, maybe an extra 15% at the high end. But I'm going to look at whether I want to make that investment or not. Okay, let's look at a couple of other houses. Well, maybe what we'll do is just take a little break here and come back for part 3.